Today, for Chem 214, we're going to review material for Exam 6. My Chapter 17 in your textbook is Chapter 19, titled Chemical Thermodynamics. And this chapter is basically dedicated to the second law of thermodynamics, the one that speaks to what is a spontaneous reaction, or why do reactions occur. The first law of thermodynamics is one that was covered in the first semester under the topic of thermochemistry. So we're going to focus on the second law, and the key word in this topic is entropy. So what I want to do, there are two review documents in Blackboard that you could use to review for this exam. And having gone through both of them, I see that there are parts of each that I would like to hit. So I'm gonna start off, actually go backwards. I'm gonna start off with the version 2 of the review document, and we'll run through it, and then we'll go to version 1. So I need to share, and I believe this one is it. There we go. So let's make this one bigger. That should be visible. All right. So the first one I picked out was question number 2. There we go. And I better keep track of these. This is version 2, number 2. Okay. A 2-bulb flask contains 5 particles. What's the probability of finding all 5 particles on the left-hand side? So we've got these 2 particles, 2 bulbs. And let's say the valve is open already. Now, it doesn't matter where they are to start with, these particles. So we just put them on one side to begin with. A, B, C, D, E. Okay, those 5 particles could spread out in various ways. Remember, we call them microstates. Each particular arrangement is a microstate. But what we want to know is the probability of finding all of them on one side, on the left-hand side in this instance. The best way to approach this is with fractions. Now, let's do one particle at a time. What's the probability of finding 1 particle on the left-hand side? Well, it could either be here or it could be there. So the probability is 1 in 2, or 1/2. Okay. What's the probability of finding the second one on either side? It's also 1/2. But if we find the second one over here and this one over here, that's a different probability than the reverse. So we have to multiply the probability of finding this one, because it could be over there, but we want a probability of being over here. So it's also 1/2 that one. So you see the trend. How about C? It's also 1/2, but to find it over there with the other 2 is the multiplier of those. And we just go on out. 1, 2, 3, 4, 5. All right. So you may be able to see the pattern here. This is 1 times 2 to the 5th. 1 divided by 2 to the 5th. All right. What's 2 to the 5th? Let's see. It's 32. So what is that in terms of percentage? Well, if we get our calculator out, and say 32 and just invert it times 100. All right, so we could say 3.13%, or that's pretty close. That's the probability of finding all 5 of them over here on one side. The probability of finding them on the other side would be the same. Okay, so that would be C. All right, that was number 2. Now I want to go down to number 14. One more page. Here we go. Oops, too far. So there's 14. So what does 14 say? Fourteen says, for the process of CH214 solid converting to CH214 liquid, the standard enthalpy of that change is 9.19 kilojoules per mole. The standard, excuse me, the standard entropy is 43.9 joules per mole K. What's the melting point of chloroform? Okay. So let's put what we know up here. What's the delta H? The delta H is 9 point, and that, by the way, that compound is chloroform. Right? They used to use it as a surgical anesthetic, but I imagine it can be hazardous. So we know that delta H 0 equals 9.19 kilojoules per mole, and the delta S is equal to 43.9 joules per mole K. Notice the difference in units here. Delta H enthalpy is in kilojoules, and delta S is in joules. That's typical to have these in different units than the other one. So what's the melting point? So what we want is the temperature at the melting point. Let me see. All right. We know that delta S surroundings equals minus delta H over T, correct? The entropy of the surroundings is related to the enthalpy by this formula. Now, when is this equal to the delta S of the system? Why? Because when we go from this, like that, oops, sorry, 3 in the wrong place. I got to write chloroform. There to liquid. We know that when you go from this to that, this is our system, this change right here. And heat transfer to accomplish that has to come from the surroundings. So we could calculate this for the surroundings at any delta H and temperature. But what's unique about equilibrium is that at the equilibrium point, when you have both solid and liquid together, and you're going through a phase change, the delta S surroundings is equal in magnitude, opposite in sign to that of the system. Okay, so now we have something we can work with. Refresh my memory here. All right. So what's the delta S of the system? Well, this is it right here. Remember, anytime we don't write down here any subscripts, this is system. And in fact, that also is system. So what we can do is we can use these two values to give us the temperature, because we know that we're at the melting point. So this value, and we have to use the same units of measure. So what is this in joules? Let's just change this one to joules. Kilo means 10 to the third. Okay, so there you go. Now if we use this formula, we find that this value, 43.9, is equal to that value, 9.19 times 10 to the third, divided by the temperature. So the temperature now is this value divided by that value. (9.19) to the third power, and 43.9 divided. So that's 3 significant figures, 209 keg. All right. But notice the answers are in Celsius. So we got to convert to Celsius. So what do? When you've got K, you subtract 273. All right. And I should be able to do this with my head. Minus, that's bigger than this one, so it's minus 64 degrees Celsius right here. Okay, that was 14. Get that out of my way. Now I want to look at 20. Okay, for 20, which I haven't arrived at yet. 20. Here we go. In which case must a reaction be spontaneous at all temperatures? Okay. So we're looking for the case for spontaneous at all temperatures. So, how do we know spontaneity? Well, the first instance we encountered in determining whether a reaction was spontaneous was the entropy of the system, of the total, delta S total. But we're introducing here the idea of temperature, right? So the entropy, that formula doesn't address temperature. What does address temperature? Gibbs free energy equation. That one right there allows you to determine spontaneity at given temperatures. All right. So what do we need to determine to be spontaneous? If delta G is negative, right? If delta G is negative, then you have a spontaneous reaction. All right. So under what conditions will delta G always be negative? To guarantee a negative value for delta G, this term here has to be negative, and this term has to be negative. If they're not both negative, then the size of each determines whether it's spontaneous. But we want something that's spontaneous no matter what the temperature, right? So if this one's negative, then how do we get negative here? Delta S must be positive. Delta S has to be positive, and delta H has to be negative. So let's see which one satisfies that. Delta H is positive. Nope, that didn't work. Delta H is 0, and delta S is negative. No, delta S can't be negative. Delta S is 0, and delta H is positive. No, that won't give you a negative either. Delta H is negative. Delta S is positive. That's your answer right there. Under those conditions, the reaction will always be spontaneous no matter what the temperature. Now, does that say anything about how fast the reaction will go? Just because it's spontaneous doesn't mean it's going to happen in your lifetime, right? Okay. But it is thermodynamically favorable. That was 20. All right. How about 26? Oops, too far. There we go. 26. Okay. When a stable diatomic molecule spontaneously forms from its atoms. Oh, this looks familiar. Didn't we cover this in the lecture? I think we did. So what does it look like? Right? So a diatomic molecule would be something like this. And it spontaneously forms from its atoms. There you go. So what are the values of delta H, delta S, and delta G? Okay, look at the question. Spontaneously forms. What does that mean? That means this one must be negative. There's no two ways about it. Okay. How about delta H? We're going to leave delta S to last. Well, typically what happens is these two atoms are separate. If they spontaneously come together, that's advantageous. Then they're the energies that they have separate decrease as they become a molecule. In other words, heat is released. So that means this one has to be negative. Okay? How about delta S? What happens to delta S for the system? Correct? Well, you got 2 moles of gas over here. You got 1 mole over there. So you're decreasing the disorder. You're going from 2 to 1. It's more orderly. And that's a negative, right? More disorder is positive, less disorder is negative. So they're all negative. That's why C is the answer. E. E is the answer. All right, that was 26. Let's see if I got any more marked in version 2 of the review document. Oh, yeah. I got 31 marked. Want to take a look at 31. Okay. So what does 31 say? Here we go. 31 is asking us to calculate the KSP, the solubility product, for sodium chloride at 25 degrees. So the question is, what's the KSP of sodium chloride at 25 degrees C? All right. Given these values of the delta G of formation, right? So, 25 degrees, remember, 25 degrees is standard temperature. So this delta G0 is appropriate. That is under standard conditions. So how do we determine the delta G, right? What do we need to determine KSP, right? How do we determine the K? Remember when we said delta G equals delta G0 plus temperature log Q. Remember that? Right. That's true. But what if Q is K? What if we are at equilibrium? What does that mean for delta G? Delta G for the particular circumstance is 0, right? A system at equilibrium has no reason, it has no drive to change. It's perfect right where it is. So equilibrium, delta G, is equal to 0, which now is equal to delta G 0 plus T log K. At equilibrium, Q is not Q anymore, it's K. It's at equilibrium. Okay. So now let's solve this for delta G. So it should be delta G 0 equals negative. Did I do that right? Left out a value. R. Sorry. Gas constant. RT log K. Right. So now, if we can find out what delta G is, we know what R is. We know the temperature, 25, right? We can solve for K. We just need to know what is delta G under standard conditions. And in order to do that, we have delta G for, let's see, how do we put that? Right, delta G 0 equals the sum of the delta G's for delta G's of formation for products minus the sum of the delta G's of formation for the reactants. Okay? So we just need to use that information, right? What are we saying? Where's the equation? Right? We know we need this, but we don't have our equation yet. So what's the solubility product? Well, it's sodium chloride is in equilibrium with sodium aqueous plus chloride aqueous, and this is solid. Okay, so do we have the information we need? There's sodium chloride, delta G. There's chlorine, chloride, aqueous, and there's sodium aqueous. Okay, we got everything we need. We just now need to plug in the numbers. So what are the products? Well, you've got sodium ions and chlorine ions. Got to add those together. Right. So delta G 0 equals, put these together, sum them up, minus 262, and then minus 131. Okay, then we'll subtract the reactants, which is sodium chloride, minus 383.8, minus 383.8. Right, and those have units, kilojoules per mole. Okay, so what we need to do is watch our signs very carefully. So this is 262, change the sign, and then 131 subtracted from that. Then this is minus minus, so that's a plus, 383.8. And I get minus 9.2. Is that right? Well, that's delta G. Okay, we know delta G, but now we need to calculate K, right here. Okay, so we got that one done. It's a stepwise process. So let's solve it for K. Now, we can solve it for natural log K. So that would be delta G divided by minus RT. Okay, so we got the delta G over here. It's minus 9.2 kilojoules per mole. And then minus R. What's R? 8.3145. Joules per K mole. And then the temperature is 25 plus 273, which is 298. Okay, what's wrong with this picture? That's joules, that's kilojoules. All right, so we need to make a change. Either change this one to kilojoules, that one to joules. I vote change kilojoules to joules. So if we take this and put it over here, times 10 to the third. So it's this number times 10 to the third. Then divide by that. Now I can divide by 8.3145. I have to change the sign because it's negative. And then divide by 298. So I get the wrong answer. What did I do wrong? The G. Oh, I'm not finished yet. What is that value equal to? Log K is 3.713. Okay, now we need to find K out of that expression. So it's E to that power. K equals E to the 3.713 power. Let's see, where is it? Here it is. So rounded off to 2 places is 41. That's K. Remember, K doesn't have any units. That's solubility product, KSP. There you go. KSP is 41. All right, that was 31. Let's see, how about 34? Go. So let's make some room. $34. There we go. All right, 34. Consider the gas phase reaction. Okay, nitrogen monoxide plus 1/2 oxygen yields nitrogen dioxide. And we're given the enthalpy. The standard enthalpy is minus 56.91, which means exothermic. And K is 1.46 times 10 to the 6th at 25 degrees. So the question is, if we raise the temperature, what effect will that have to do at equilibrium, what effect will that have on the amount of NO? All right. You can take two approaches to this. And the simplest way to answer that question is with this reaction, okay, yielding NO2 gas, and we know that it's exothermic, minus 56.91 kilojoules. If it's exothermic, then where's the heat going to go? It's going to come out of the reaction. So it'll be 56.91 kilojoules. Okay? Now, what happens when you raise the temperature? Raising the temperature adds energy to this side, correct? We're using Le Chatelier's principle to answer this question. We don't have to go in and do any fancy calculations. Add energy here, and it drives the equilibrium back this way. So it will increase the amount of NO. That's why the answer is A. Okay? So, we didn't even have to know, well, with all the other wording in the problem, we did need to know that delta H is negative, right? So that's the key right there, that negative value. Tells you it's exothermic, which means it goes over here. Then you can use Le Chatelier to say it goes backwards. All right. Okay, that was 34. Very simple. How about 40? The second law of thermodynamics states what? Energy is conserved in a spontaneous process. No, it doesn't say anything about that. The entropy of the universe increases during a spontaneous process. That is true. In any spontaneous process, delta S is greater than 0. It's always increasing for the entire universe. Or, actually, you could say this. Delta S total is greater than 0 for any spontaneous process. Okay? Both are correct. This one works no matter what happens in the universe. Everything taken together, that always increases in the universe. But for an isolated system and surroundings, it only happens when the process is spontaneous. Right? When it's positive, then the process has to be spontaneous. And that's just another way of giving you the second law of thermodynamics. Let's see, that was 40. 42. I must have seen something in 42 that piqued my interest. Okay, 42 is going to take a little work. So let's see what it is. A mixture of hydrogen and chlorine remains unreacted until it is exposed to ultraviolet light from a burning magnesium strip. And believe me, when magnesium strip burns, it puts out a lot of high energy ultraviolet light. So you don't want to look at it for more than a blink. Then the reaction occurs very rapidly. Well, that doesn't matter. Not in thermodynamics. The rate of the reaction doesn't matter at all. But we're given these values. Here's the balanced equation. All right. Here are the values that are associated with that reaction. Delta G, delta H, and delta S. Which of the following statements is consistent with this information? All right. So we have to understand, what are they trying to say? The reactants are thermodynamically more stable than the products. Well, let's see. Is that true? If the reactants are more thermodynamically stable than the products, then the reaction is not spontaneous. Correct? If the reactants are more stable, then they don't want to be products. What do these values actually say about the reaction? Delta G is negative. That means the reaction is spontaneous. And that means it wants to be product, not reactant. So A has to be false. A can't be true. Well, not capital. Do small. So that's false. Why? Because delta G is negative and delta H is negative. Delta S may be negative, but overall, when you incorporate, when you use, you don't have to use Gibbs free energy law here, or his equation, because you're already given the value of delta G. This reaction is spontaneous, which means the reactants are less thermodynamically stable than the products. Okay, let's go to B. The reaction has a small equilibrium constant. All right. Is that true? Well, these should all be delta G 0, delta H 0, delta S 0. That's a mistake. Because in order to answer this question, we need delta G 0 equals negative RT log K. And we're going to solve this equation for K again. Right? So let's put everything in terms of joules, because entropy is in joules. Well, actually, not because entropy is in joules, because this is in joules. Right? So that will be negative 45.54 times 10 to the third. And this is a negative 8.3145 joules per k-mole. The temperature would have to be 25 degrees, or 298. And then log K. So now let's see if I can do it right this time. Divide both of these into that one. And 8.3145 divide, and then 298 divide. So I get 18.38. Right? So K is going to be e to that power. which is 9.6 times 10 to the 7th. All right, so let's answer the question. The reaction has a small equilibrium constant. No, it has a huge equilibrium constant. So B is false. How about C? The ultraviolet light raises the temperature of the system and makes the reaction more favorable. Oh, yeah? It doesn't raise the temperature, but it does do something. It provides activation energy, right? You don't have to raise the temperature to reach the activation energy. You can provide that energy by other means. And in this case, we're using ultraviolet light to provide the activation energy. And then once you reach the activation energy, once you get the reaction started, then it provides enough energy for the rest of the molecules to reach their activation energy. How do we know that? Because the reaction is exothermic. So one molecule reacts, gives off energy, that's enough for the next molecule to go, and it's a cascade. So C is false. All right, we got D and E left. The negative value of delta S slows down the reaction. Okay, the key here is slows down the reaction. Thermodynamics says nothing about the speed of a reaction. Slows down a reaction? We don't know. The delta S says that the product, the system after the reaction, is more ordered than the system before the reaction. So D is false. That only leaves E. Let's see if it's true. The reaction is spontaneous. Yep, delta G is negative, but the reactants are kinetically stable. All right, how do we determine that? The first part is true. The reaction is spontaneous. We know that because delta G is negative. But with the description of this problem, can we say anything about the kinetics of the reaction? Well, yeah. When we say kinetically stable, that means the reactants are not going to do anything until they're pushed to do it, right? And that means supply the activation energy. When we supply the activation energy, then the reaction goes. But up to that point, the mixture of hydrogen and chlorine remains unreacted until, that means it's stable. So hydrogen and chlorine in the same vessel are stable. They're not going to react until we supply the activation energy, some form or fashion. In this case, ultraviolet light. In other cases, maybe heat. Right? What else could we do? Well, it's not in the problem, but we could add a catalyst. And then the temperature alone may be sufficient activation energy to start the reaction. But E is true. We know the reaction is spontaneous, and we surmise that the reactants are stable kinetically because we have not reached the activation energy that was provided by the ultraviolet light. Okay, 42 took a while, I understand, but There's some good information there. Let's see if we got another one coming up. Yeah, 52. There we go. 52. Okay. The equilibrium constant of a certain reaction was measured at various temperatures. Okay. We know that the equilibrium constant is going to change with temperature. Now, look at this graph. What are we plotting? We're plotting the inverse of temperature against the log of K. Remember that formula came toward the end of the lecture. Log K equals negative delta H sub 0 divided by R times 1 over T, and then plus delta S 0 divided by R. Okay, remember that equation? If you plot 1 over T on the x-axis, right here, and log K on the y-axis, y equals slope of the line, x plus y-intercept. Okay? So, based on that information, we can look at this graph and say, all right, first of all, what's the question? What is delta S0 for the reaction? We want to know this one right here. So what do we need? We need the y-intercept. So what's the y-intercept? Well, look, right there. It's 3. So the y-intercept is 3.0 is equal to delta S0 over R. Now we can calculate delta S because we know what R is. R is 8.3145. So we say this one times that one is delta S. Well, 24.9, rounded off is 25. 2 places. Okay. Well, that's in joules. Joules per mole K. All right. So that's why the answer is C. Now, do you have to memorize that formula? Well, let's see. There should be useful information in the same folder as the exam. So that's what you need to print out before you open the exam in Lockdown Browser. That way, you'll have it with you. But it's okay to use that useful information and a periodic table, whatever else is in that folder identified as useful information. It's legal for you to have that. And that will have the formula in there for you. You just have to recognize it for what it is and know how to use it. Okay, that was 52. Okay, let's see. Is there any more in this? Oh, yeah. 56. So I just used that one. I want this. Here we go. 56. Here we go. Okay. The equilibrium constant K sub P. So K sub P is in is calculated from units of pressure, partial pressure, which is fine because this is for the dissociation reaction of dichlorine to two chlorine atoms. Okay. The K was measured as a function of temperature in units of K. And a graph of log K versus 1 over T for this reaction gives a straight line with a slope, gives you a value, and an intercept gives you a value. Right? So we go back to that same equation, don't we? In this case, where log K sub P equals negative delta H0 over R times 1 times inverse of T plus delta S0 divided by R. Okay, we're given this information, the slope of the line and its y-intercept. Now, is delta H going to be, can we calculate it from this? Well, there's delta H. Do we need the y-intercept? No. We don't need the y-intercept. There's no delta H in there. What we need is the slope. So this value, negative 1.651, negative 1.651 times 10 to the 4th is equal to the slope of that line. Correct? That is equal to negative delta H0 over 8.3145. Okay. What we're going to do is take this negative together with that number and multiply it by that one. Okay, so that's 1.37 times 10 to the 5th. 1.37 times 10 to the 5th. What are the units here? Right? If that's K, and this is joules per K mole, then this value has to be in joules. Well, what's the answer? The answer is in kilojoules. So how much is this in kilojoules? Well, 10 to the 3rd of that would be kilojoules, right? 1.37 times 10 squared kilojoules, and then move the decimal 2 places to the right, 137 kilojoules. Positive. So there's your answer right there. So what type of reaction is this? If delta H is positive, it's endothermic, correct? It's endothermic. Right. Okay, that was 56, was it? Yeah, 57. I want to take a look at that one also. Okay, 57 says for a certain process at 300 K, so the temperature is 300 K, delta G equals minus 12.2 kilojoules. Delta G equals minus 12.2 kilojoules.
and delta H equals minus 7 kilojoules. I'm pretty sure that these are not standard conditions because it says at that temperature. Right, so we don't have a 0 here for that reason. This is not standard. This is the actual values at that temperature. If the process is carried out so that no useful work is performed, delta G is what? No useful work is performed. Delta G is what? Well, all delta G says is the maximum amount of work that can be obtained. Right? The maximum amount of work that can be obtained is minus 12.2 kilojoules, whether you do it or not. If you don't do it, then delta G didn't change. Delta G is still there. It's just you didn't get any work out of it. In other words, the work, the actual work, this is the maximal amount of work that can be extracted. Now, if you're actually measuring the work, well, it says the actual work is equal to 0. But that doesn't change delta G. Delta G for that reaction is the same, whether you get work out of it or not. So it's kind of a trick question. The value is here. Minus 12.2 kilojoules is delta G. Right? Okay? That's tricky. Tricky question. All right. So that's it for, those are the only ones I selected out of version 2. Now I want to go to version 1. And there's some problems in version 1 that are valuable for us to review. There we go. This is version 1. And we're going to start version 1 with number 9. There we go. Version 1, number 9. Okay, that's not number 9. There's number 9. All right, at 1 atmosphere, liquid water is heated above 100 degrees. Right? So we're not at the boiling point, we're above. So we don't have any, if we're heating water above 100 degrees, that means that we're not at equilibrium anymore. So the question is, what's the delta S of the surroundings? If water is heated to greater than 100 degrees. Right. That's what we're saying. At 1 atmosphere. Right. 1 atmosphere. Then what's delta S of the surroundings? Right. Well, we know delta S, one formula for delta S is minus delta H over T. And we know that the process is endothermic, right? When you heat water, when you add water in there, heat's coming in from the surroundings, it's endothermic. That means delta H is positive. Correct? Delta H is positive. Because we're always talking about, without a subscript, delta H is for the system. So if you know the delta H for the system, and you know the temperature, you can calculate delta H for the surroundings at any temperature. It doesn't have to be at the boiling point or the melting point or during a phase change. So, what, to answer the question, they're wondering what's the sign on delta S surroundings. Is it greater than 0, less than 0, equal to 0? Not enough information, or none of the above? Well, if that's positive, and temperature is Kelvin, it's always positive. So positive times a negative means negative. So the sign on delta S, surroundings, is negative, less than 0. Okay, that's B. Oh, I'm going to do 10 also, using the same system. So let's just change this to 10. Okay, and we have a similar situation. Right. Now we want to know what's the delta S of the universe. And I think in these terms, we're thinking delta S total. Delta S. Delta S total is equal to delta S system plus delta S surroundings. Right. Okay. If this were equilibrium, that would be 0. Right? 0 at equilibrium. But like I said before, we're not at equilibrium. We know that this is negative. Now, when we add energy to the system, that makes this one positive. So this one's negative, and this one is positive. All right. So the actual sign of this one depends on which one of these is larger, correct? Right. So if we can determine from some process of logic which one of these for that process is the larger one, then we can say something about this one, because it's not at equilibrium. It's not 0. It's either negative or positive, because we're not at equilibrium. All right, look at it this way. When we are at equilibrium, where is the energy going? The energy is going into phase change. But now we're above that temperature. So the energy that you're adding to the system is greater than is required to break the intermolecular forces that are holding the molecules together. Now what you're doing is adding energy entropy. You're adding more energy entropy than is required. So that tells me that this one is bigger than that one. You're adding extra energy. You're making the system more disordered. And that means if this one is greater than that one is also going to be positive. Okay? That's how we reason it. So that's why it's greater than 0. All right, that was number 10. 11. How about 11? There we go. 11. It looks worse than it is. Which of the following is true? All right. By spontaneous, we mean what? That a reaction or a process will always proceed to the right, even if very slowly? Well, yeah. So let's see which ones of those are actually say that. By spontaneous, we mean reaction will always proceed to the right as written, even if very slowly. Okay. What does B say? By spontaneous, we mean the reaction or process will always proceed to the left? No. That's wrong. Will always proceed to the left for C? Nope, that's wrong. D. By spontaneous, we mean the reaction or process will always proceed to the right, even if very slowly? That's true. So A and D are possibilities. Let's see, because E says none of them are true. So maybe both A and D are false. Well, let's see what else they got to say about it. Increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. Well, how about this? When you mess with the temperature, you mess with delta G, which is spontaneous. So A is false. When you increase the temperature, actually when you do anything with the temperature, you affect the spontaneity of the reaction. Maybe positive, maybe negative. It depends on other factors. Well, let's see if D is okay. Increasing the temperature may speed up the reaction, and it generally affects the spontaneity of the reaction. That is true. It may speed up the reaction. Right? Doesn't have to, but it will affect the spontaneity of the reaction, right, because of this equation. But the speed of the reaction depends on whether the reaction is exothermic or endothermic. Well, actually, it depends. The speed of the reaction depends on activation energy. Okay. So increasing the temperature may speed up the reaction, but it does affect the spontaneity. So D is true. D is the answer to number 11. All right, let's see what's next. I know there are more. Oh, not on those pages. They must be duplicates from the other version. I don't like to repeat myself if I can help it. Although repetition is good. It gives you practice. 34. So let's scroll down fast to 34. Oops, there it is. Okay. So 34 says what? The following reaction, carbon dioxide plus water yields methane plus oxygen with a delta H, standard delta H of 803 kilojoules. So what does that mean? That means this reaction is endothermic. We have to add energy, right? You know what it looks like to me? It looks like the reverse of methane combustion. Methane plus oxygen yields that if we go the other direction. Which of the following will increase the K? All right. All right, let's write that reaction out first. So we have CO2 plus 2 water, CO2 plus 2 water, yields CH4 plus 2O2. And the delta H0 is 803. There we go. Okay. Now, notice that they're all gases. Everything is a gas. Gas, 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 gas. So that means every term goes into the equilibrium expression. Right? There are no pure liquids. Like water is a gas here, it's not a liquid. So we have to say the expression here, the K, is equal to methane times oxygen squared divided by carbon dioxide times water squared. Okay, we know that's true. So let's see if we have enough information to answer these questions. Which of the following will increase K? Well, the first option is decrease the number of moles of methane. A. Decrease methane. Will that change K? No. It'll change the equilibrium position, but it will not change the value of K. K only responds to temperature. Increase the volume of the system. Same thing. Increase volume. If we increase the volume, then which way is it going to shift? Well, let's see, there are 3 moles here, 2, 3. It's not going to move at all. Nothing will happen, right? Actually, in my worked problems, that's wrong. I said increasing the volume of the system will shift the equilibrium concentration, but will not affect K. Well, it's true, it won't affect K, but it won't shift the equilibrium either, because there are 2 plus 1 is 3 and 2 plus 1 is 3. Did I get that right? Yeah. So that won't change it. The volume won't change the equilibrium position either, and it won't touch K. Increase the temperature of the system. Increase temperature. So what happens if we increase the temperature? Does that affect K? Well, we want to know, does it increase K? What do we know about temperature and K relationship, right? That formula that we looked at earlier. Okay. If we have log K and 1 over T, then the slope of the line is going to be negative delta H over R. Negative delta H over R. Okay, we know that, right? That's the way the line, that's the way the cookie crumbles. Well, with 803 kilojoules as delta H, 803 is positive. That's where we're sure that the slope is negative, right? If this were a negative value, if it were exothermic, then the line go the other way, right? Because a negative times a negative is a positive slope. So we know that the slope is negative, right? Now that we've characterized that slope, what happens when we increase, is that right? Increase K. Increasing K does what to log K? It increases log K also, right? So log K increases. So as we increase log K, what happens to 1 over T? Right? It's this way. So as we increase log K, we're decreasing 1 over T. Right? So what does that mean for T? Well, look, if you're decreasing this value, what's T have to do? In order to make the inverse get smaller, T has to get bigger. So increasing K corresponds to an increasing T. Right? Increase the temperature, you will increase K under these circumstances. So this one is true. And D and E, well, they just kind of drop out because C is true. So D and E don't matter. We only had to evaluate A, B, and C. How about 36? Okay. 36. There it is. So what about this gas phase reaction? That looks familiar. Yeah, we calculated. Okay, we can answer this one. So if we have N plus 1/2 O2 and O plus 1/2 O2, and these are all gas phase, right? Look at the first statement, gas phase reaction. That means all of them are gases. And that leads us to NO2. NO2. Okay? Delta H is negative 5691. Negative 56.91. And we'll just put K in here. K equals what? 1.46 times 10 to the 6th at 25 degrees C. Okay. What would be the effect on the amount of NO? This one. Of compressing the equilibrium system to a smaller volume. And the temperature remains constant. So this is another Le Chatelier's question. If it's at equilibrium, then what do we need to establish to say that something is going to change in this reaction when we compress, decrease the volume? If you decrease the volume, what's the system going to do if it can? It's going to make fewer moles, right? Somehow. So how does it make fewer moles? Well, this side is 1 mole, this side is 1.5. So when you compress it, it's going to move to the smaller number of moles, which means you consume NO. So the amount of NO will decrease under these conditions. Okay? I think before we changed the temperature, right, in this type of problem. But in this one, we increase the pressure, decrease the volume. All right. So that was 36. Let's see if I got, what else do I have marked here? 46. So 46 is on the menu. Okay. Oops, got to go farther. There we go. That's the last one, so I better stop right there. Okay, we're given the following data. Calculate the normal boiling point for formic acid. So what would the normal boiling point look like? Well, the transition is going from, oops, that was given out on me. Let's try this one. Liquid to gas. Okay, that's what it looks like. Okay, so what's the question? The normal boiling point. So what do we know about the boiling point? Well, for the system, 46. Yeah, 46. For the system, delta S, right, equals delta H over T. And when they say normal boiling point, that's 1 atmosphere pressure. 1 atmosphere. Now, why can I say this? I can say this because at the boiling point, the entropy of the system is equal to the entropy of the surroundings. The surroundings would be negative delta H over T. The system would be positive delta H over T. Okay, so we need to determine what's the delta H of that reaction. And what's the delta S for that reaction. Right? So they're similar formulas. They're based upon these values. So the delta H would be, for that reaction, would be the standard enthalpy of formation for this compound minus the standard enthalpy for this compound. Well, actually, yes, that's correct. I'm sorry. I had a brain freeze for a moment. So what's the standard enthalpy of this one minus that one? The standard enthalpy of COOH gas is minus 363. Minus 363. And then minus the reactant, which is minus 410. Right? So minus 410. So the delta H for this reaction is, well, it's going to be a positive number. Forty-seven kilojoules. Okay. How about delta S? Well, we follow a similar pattern, right? This one, gas, 251.1 minus 130 for the liquid. Okay. And that value is what? $121.1. Positive. 121.1 joules per mole K. Okay. Now we have those values. What we need to do is change this one to joules so that we can use that formula. So delta S is going to be um, 121.1, and then this is 4.7 times 10 to the fourth joules per mole, and this is joules per kmol, and that's divided by T. So how do we get T out of that? Well, T comes over here, and this one goes over there. So it's this one divided by that one. Let's see. Right. I get 388 Kelvin. Minus 273 for degrees Celsius right here, see? It has to be degrees Celsius for us to find the right answer. 273. So that's 115 degrees C. Okay? So, formic acid has a higher boiling point than water. All right, that was 46. Oops, I didn't write that up here. 46. Okay, let's see what else is in store. 52. 52. This is going to be a kissing cousin, I think, of Hess's law. Probably. All right. So our target reaction is water gas plus half oxygen yields hydrogen peroxide, right? And at 600.1 degrees, or actually 600.1 K, and use the following data to determine what? Delta G0. Right? So how can we get K out of that? Well, we know that delta G0, the relationship between delta G0 and K, we know that. Let's write it up here. This is number 52. Delta G0 equals negative, I think that's right. Yeah. Negative RT log K. So we need to know the temperature, which we know. We need to know R, which we know. We need to find out what K is. Right? So how do you get K out of this? Well, we're given these two reactions with their Ks, and if we use Hess's law, we can combine them, supposedly, to make the target reaction. So H2 plus O2, H2 plus O2 yields H2O2, H2O2 gas. And the K for that one is 2.3 times 10 to the 6th. 2.3 times 10 to the 6th. Okay? Now, I forgot to write the target reaction. Where we're headed is water plus 1/2 oxygen yields H2O2. Okay. So we've got hydrogen peroxide on the correct side. What we need is water. So here we have hydrogen and oxygen on the wrong side because we need to put water on the other side. So if we invert the equation and put water on this side, and that's 2 hydrogens plus oxygen, then what would the K be? The K would be the inverse, right? When you invert the equation, you invert the K expression. So it'd be the inverse of 1.8 times 10 to the 37. So it's 1 divided by 1.8 times 10 to the 37. All right? All right, but let's see. We need one of these. We got that. One of those. We need 1 water and 1 hydrogen and 1/2 an oxygen. So what if we took 1/2 of this equation? That would give us 1 water. That would give us 1 hydrogen, which would cancel this hydrogen, right? There's no hydrogen up here. So we got to cancel the hydrogens. And the oxygen now is 1/2, right? So this 1/2 of oxygen takes 1/2 of that one away. Right? So these two together give us 1/2 an oxygen. These two together give us nothing, and then 1 water. So there's 1, and there's 1. So we got the right equation. We just need to do what with this one? Well, when you multiply the equation by a constant of some kind, that becomes the power of K. So we got this new K here, which is the inverse. Now we're going to take it to the 1/2 power, right? That'll give us this K. Now, what's the combination of the two? You multiply them together. So first we need to take the inverse of this and then take the square root. That's what 1/2 power means. So 1.8 10 to the 37th. Do the inverse of that, right? So that's 5.56 times 10 to the minus 38. And then we take the square root of it, which is 2.36 times 10 to the minus 19. And then we multiply it by 2.3 times 10 to the 6th power. That's 5.42 times 10 to the minus 13. That's equal to our K. All right, now we can put this K in here, along with 600.1 here and 8.3145 here. And yeah, we'll take the natural log of our K, and then we find out delta G. Okay? So let's erase some of this so we can put that information up here. All right, so delta G, 0, is equal to negative 8.3145 times 600.1 times the natural log of 5.42 times 10 to the minus 13. Okay? So I'm going to start with the natural log because I've already got this number in my calculator. So I'll just take the natural log of it there. And then we're going to multiply that times 600.1. And then we'll multiply it by 8.3145. And there's a negative, so we got to change the sign. All right. So G is, let's see, which one are we on? 52? Yeah. Yeah. It's in kilojoules. So what I've got so far is 1.41 times 10 to the 5th. 1.41 times 10 to the 5th. And because of this here, that's joules. So that would be 1.41 times 10 to the 2nd kilojoules. Or, move the decimal place, 141 kilojoules. Okay. That took a lot of work, but we got there. 53. 53? Yeah, 53. So let's move it up just a little bit. There we go. And let's just write this over again. Version 1, number 53. Okay. So we've got this equation. 2 nitrogen dioxide gas yields N2O4, dinitrogen tetroxide. The delta H is negative 56.8, so it's exothermic. And delta S for the system is minus 175, right? So it becomes more ordered. And that makes sense, actually. 2 moles here, 1 mole there. So you would expect some order out of this reaction. All right. So in a container at 298, which is standard temperature, N2O4 and NO2 are mixed with initial partial pressures of 2.4 atmospheres and 0.42 atmospheres. Which of the following statements is correct? Right? Some N2O4 gas will decompose, some NO2 will dimerize. The system is at equilibrium. All right. So in order to determine that, to determine which way the reaction will move, we need to find 2 things. We need to find the K, right? What's the equilibrium constant for this reaction? And then we need to find out what's the actual Q for the reaction. All right? K is going to take a little work. So let's write the reaction up there. And those are both gases. Okay, so we're going to do delta H and delta S. Okay, here you go. We want to find K, that's the equilibrium constant, right? So we can say that delta G0, which is equilibrium, is minus RT log K. Right? We just need to find out what is delta G. Well, where do we know delta G in terms of enthalpy and entropy? Gibbs equation. Delta G0 also equals delta H0 minus T delta S0. Okay? And we're given those two values. Delta H is right here, and delta S is right there. So we can calculate delta G. But then we'll use delta G to calculate K. Well, why not make it easy on ourselves? Let's just do one calculation. If this is equal to that, and that's equal to that, then this is equal to that. Right? Minus RT log K is equal to delta H0 minus T delta S0. See with it? If A is equal to B and B is equal to C, then A is equal to C. That's what we did there. A is equal to C. Okay. So let's simplify this. Let's put it in terms of log K. Log K is equal to delta H0 minus T delta S0 divided by negative RT. Okay? So now all we have to do is put values in there and solve for K. So what are the values? Well, let's see. Delta H is in kilojoules. It needs to be in joules, right? Because delta S is in joules. So minus 56.8 kilojoules would be minus 56.8 times 10 to the third joules. And then we subtract from that the temperature, which is 298, right, times delta S, minus 175, minus 175. Okay? Then we divide by negative R, 8.3145 times T, 298. There. Okay. Now we just need to resolve that expression. All right. So let's subtract 175 from 298. Oh, excuse me, not subtract, multiply. $298, and then 175, change the sign, times. All right? That's minus 5.2 times 10 to the fourth. And then subtract it from 56.8, change the sign, exponent to the third power. And then minus. So I get minus 4.65 times 10 to the third divided by this expression. So 298 divide and 8.3145, change that, divide. So that's, so log of K equals 1.8 767. So K is equal to E to that power. So I get 6.53. I'm just checking to see if I'm on track. 6.53 is K. All right, now we have K. Now we've got to calculate Q. So what's Q? Well, what are we given? We're given, well, I'm looking at the wrong one. The initial partial pressures are 2.4 for N2O4. Look how it's written. In a container, N2O4 and NO2 are mixed. Initial partial pressures are 2.4. So that's N2O4 is 2.4 atmospheres. And NO2, see, they're not giving it in the order of the reaction. They're giving it in the order in the sentence. 0.42 is NO2. Okay. So Q would be N2O4 divided by NO2. Notice I'm using parentheses and not square brackets. There. So this would be N2O4 would be 2.4 divided by 0.42 squared. All right. So what is that equal to? Let's square 0.42 first. And then 2.4 and divide the former one into that. 2.7 times 10 to the minus 2. So there's Q. So what do we have? K is greater than Q. K is greater than Q. So what does that mean? If K is larger than Q, that means we have a whole lot of this. And the reaction is going back that direction. So some N2O4 will decompose into NO2. That's what that means. All right, we went a long way around the barn, but we got it answered. That was 53. Now, let me see. What's next? 56. This is running longer than I expected, but this is just a recording. I'm not keeping any students out, so I'll take as much time as required. $56, did I say? Yep. 56. All right. There it is. Consider the following system at equilibrium. At 25 degrees. PCl3 plus Cl2. PCl3 plus Cl2 yields PCl5. And they're all gases. Oh, delta H is minus 92.5. Minus 92.5 kilojoules. Okay. Well, this might be easier than I expected. Okay. Okay. So, what's the question? If the temperature of the system is raised, the ratio of partial pressures of PCl5 to partial pressure of PCl3 will what? Increase or decrease? All right. So what do we know? If that's negative, this is exothermic, and that delta H is on this side of the equation, right? That means if we, in increase the temperature, the reaction is going to go back this way. So the ratio of PCl5 to PCl3 would do what? Well, if we add heat to this side, shifts back that way. So this is going to decrease and that's going to increase. This is going to decrease and that's going to increase. So that means the ratio decreases. Right there. Right. That was pretty easy. How about 58? Ah, this is the one. We did a version of this one in the other in version 2. Let's see. With this slope and this intercept, we measured the K for this reaction at different temperatures and plotted. That's supposed to be ln K right there, not in. Log K plotted against 1 over T. And it gave a straight line with a negative slope and an intercept of 14.51. For this data, which of the following statements are true? The reaction is exothermic, endothermic. The reaction rate is high. We don't know anything about the rate, right? There's no way to tell. This is equilibrium. Or the reaction is not spontaneous. The reaction is Cl2 yields 2Cl. And the slope of the line that we plot, log K against 1 over T, the slope is this value. And it's equal to negative delta H. Okay? That value, this term is equal to the slope. All right? So what does that mean? Well, if this is negative, and we take this negative over here times that one, it's a positive. So delta H is positive. This is an endothermic reaction. Right? So B is true. Right? It can't be E because one of them is true. Right? And they can't all be true. Right? Not under these choices. So the rest of them are irrelevant. We found our answer. It's B. All right, 58. Let's see. I'm going to fry my brain some more. 59. 59. Okay. I think this one's simpler than it looks. 59. There we go. For a certain process at 300 K, delta G equals minus 10.4 kilojoules and delta H equals minus 7 kilojoules. Those two values are actual values. They're not standard or normal conditions, right? Because the temperature is 300. So if the process is carried out reversibly, the amount of useful work that can be performed is what? Well, the amount of useful work is equal to delta G. Right? This is 59. That's by definition. The maximum amount of work is equal to delta G. Right? So the amount of work that can be carried out is equal to delta G minus 10.4 kilojoules. Right? That's simple. Right there. All right. We're done. That's all I had marked off anyway. Okay, stop the share and close it out and post it.